Welcome to another explainer. Today, we're taking a truly fascinating piece of aviation engineering and breaking it down so you can understand exactly what's going on at 30,000 feet. To kick things off, I want you to just use your imagination for a second. Picture yourself sitting quietly on an evening flight. You've got your headphones on, maybe looking out the window into the dark, stormy weather brewing just outside.
And then boom, out of nowhere, this terrifying, intensely bright flash completely washes out your window. It's immediately followed by a massive, rattling bang that violently shakes the cabin. I mean, your heart skips a beat, right? As that sound just reverberates through the entire plane.
So the immediate thought racing through everyone's mind is, did lightning just hit the airplane? And honestly, more importantly, are we about to crash? Should you be terrified right now? It's a highly relatable fear and for sure a really dramatic moment to experience mid-flight. But what is actually happening to the aircraft in that exact second? Well, before you panic, take a deep breath and consider this number, 1 to 3. This might actually shock you, but commercial aircraft are struck by lightning, on average, every 1 to 3 years. When you consider the roughly 100,000 commercial flights happening globally every single day, taking a lightning hit is definitely not some one-in-a-million freak accident. It's actually a completely expected operational event. Section 1. Anatomy of a strike. Okay, let's dive into this, because we really need to understand the precise physics of what happens when a plane takes a hit. How does a massive machine soaring through the sky actually handle a direct hit from millions of volts of electricity without, completely falling apart in midair? Well, when a strike happens, it follows a highly controlled sequence. Step 1. The electrical current usually enters through a specific extremity of the plane, very often the nose or a wingtip. Step 2. The current travels, but it doesn't just go anywhere. The airplane's highly conductive outer layer acts like a brilliantly designed protective shell. This purposefully guides that massive electrical current right along the low-resistance exterior of the aircraft, keeping the energy completely concentrated on the outside skin. Finally, step 3, the lightning safely exits through another extremity, typically the tail, leaving the plane behind as the current just continues its path toward the ground. Section 2. The passenger safety bubble. So if all that raw electrical energy is coursing over the exact metal tube you're sitting inside, why aren't you and everyone else on board electrocuted? Well, the crucial point is summed up perfectly right here. Think of the aircraft as a giant protective enclosure. Because electrical currents will always follow the path of least resistance, the energy stays entirely on the highly conductive exterior of the aircraft. This creates what physicists call a Faraday cage. Inside that cabin, you and your fellow passengers are completely isolated from the massive electrical current flowing just inches away on the outside. Because of this incredible feat of engineering, the reality inside the cabin is actually surprisingly anticlimactic. Passengers usually experience nothing more than exactly what we described at the start, just a blindingly bright flash and a sudden, really loud noise. There is no electrocution, there's no disaster in the cabin, just a very brief, very loud light show. Section 3. Protecting modern composite aircraft. Aerospace engineering never stands still, though, which introduces a pretty fascinating twist to this entire electrical threat. Now, what's really interesting about this transition is the contrast. Traditionally, aircraft were built with highly conductive aluminum airframes, which, is absolutely perfect for effortlessly conducting a lightning strike. But modern marvels like the Boeing 787 and the Airbus A350 use vast amounts of carbon fiber composite materials to save weight. The catch? Composites are far less conductive. So, to safely guide the lightning, manufacturers actually embed layers of highly conductive expanded copper or aluminum mesh directly beneath the outer surface of the carbon fiber. This cleverly engineered hidden layer gives these modern jets the exact same level of protection as older metal planes. Section 4. The real danger. Thunderstorms. If modern planes are engineered to handle lightning strikes so perfectly, you might be asking a pretty logical question right now. Why avoid flying through storms in the first place? Well, the real danger isn't the lightning bolt, it's the storm itself. Severe thunderstorms pack some incredible hazards. Severe turbulence that can violently throw an aircraft around, massive hail that can literally batter an airframe, strong wind shear, which are sudden violent shifts in wind direction and speed, heavy blinding rain, and powerful updrafts and downdrafts. These are genuine, severe operational risks that make for a highly uncomfortable and potentially hazardous ride. To avoid these hazards, flight crews definitely don't just guess. Pilots rely heavily on advanced onboard weather radar and continuous real-time guidance from air traffic control. They use these incredibly sophisticated tools to deliberately map out and steer clear of the most intense storm cells, prioritizing safety and a smooth ride over absolutely everything else. Section 5. Rigorous testing and certification. But how do we know all this protection actually works? I mean, aircraft aren't just built and thrown straight into the sky. Engineers literally shoot simulated lightning currents at aircraft structures to verify mandatory outcomes. And this brilliantly illustrates exactly how thorough that certification process is. Flight controls, they must continue operating correctly without a single glitch. Fuel tanks, this is critical. They must remain fully protected from any sparks or ignition. And the brains of the plane, the avionics, communications, and navigation systems, they must keep functioning safely and reliably through the entire electrical surge. Every single system must pass. Let's move on and see how this builds into the reality of daily operations. Because, actually, a massive bolt of lightning isn't a completely zero-impact event. While serious accidents caused solely by lightning are extremely rare in modern commercial aviation, strikes can occasionally cause minor exterior damage. We're talking small, localized burn marks, tiny structural punctures right at the specific entry and exit points, or sometimes minor damage to external sensors or antennas sticking out of the fuselage. But the protocol here is incredibly strict. If a strike is suspected, the aircraft doesn't just fly its next leg blindly. Following a reported strike, maintenance teams thoroughly inspect the aircraft on the ground. Any of those small burns or tiny punctures are carefully caught and repaired before the aircraft is ever allowed to return to service. This rigorous safety culture is exactly why millions of passengers safely fly through stormy weather every single year without incident. So, as we wrap up this explainer, I want to leave you with a question to ponder. Have you ever experienced a mid-air lightning strike? The next time you're flying and you see a brilliant flash of light outside your window in a storm, instead of gripping the armrest in absolute terror, you can sit back with the comforting thought that the incredible machine you are sitting inside was meticulously designed, tested, and built with this exact